Well, I am Maria Varela, he's Norbert Neves, and we're going to be your Electromagnetism I teachers, okay? So we will share the subject. I think it will be mostly me, but we'll sort of divide the subject into pieces. So we will try to the best of our possibilities to have one of us teaching like a whole block or section. So it's not like one day it's me and then tomorrow it's him or whatever, but we'll see how this goes, okay? So I guess just one question. How many of you did not pass Physics 2, the second half of Physics last year? Okay. All right. That's fine. That's okay. You will pass this year, so it's okay. Rest assured that we'll make sure. Okay. So anyhow, this is a subject that you know you will have for the first semester, and then second semester is electromagnetism. Are you going to be this year electromagnetism? Okay. Good. But he knows a lot more electromagnetism than I do. He's also a teacher of electrodynamics in the fourth year. For those of you who go into the fundamental physics part. So it's our classes, as you know, I'm just going to give you a very short overview of the general information, so you can ask questions as well, and then Norbert will get started with section 1 of the syllabus that he will teach for the next couple of weeks. Okay. So as you know, our classes are Tuesdays, Thursdays, and Wednesdays. Tuesdays and Thursdays it's 10:30 to noon. As you know, we start 10 minutes after this nominal starting time, okay? So you can have a little bit of a recess in between classes. And then Wednesdays we do 11 to 12. We will have also mentoring and sessions and office hours. I don't know about you, Norbert, but in my case, my supposed office hours are, I don't know what this is in the teaching guide, I don't care. I mean, just if you want to have a session, like a tutorial or a mentoring session, just write me an email and we can do it anytime. It doesn't have to be on these hours. So, yeah, right. So we just schedule an appointment whenever it's convenient for you and for us, okay? And then we can do it either in the office or online, or so just feel free anytime to ask for attention. All right, and forget about this. This is just something we must put in the teaching guide, but we have a lot more time for you. Okay, that is. Please, if you want to add anything anytime, feel free to do so. So, as you know, I think last year you did have a 100% face-to-face teaching, right? But this year you get started with this whatever, who knows what, mode. So this means that we will divide the class, as you know, in odd and even ID numbers. Every week you will have the chance to come, and then the next week you'll have to be at home. So from home, we will basically use or try to use, as long as it works, this Meet link for the classes. Okay, and we will also record the classes, right? So I made them available to you. So you can post them again later or something. Of course, content will be edited for sure, so we can remove the inconvenient things. We don't need everybody to know. But anyhow, you can just feel free to either come here or follow from home, or we will have some technical problems, especially the first few days, because every year they are changing cameras, projectors, and everything. So just like today, we apologize, and please bear with us, okay?
I would like to add that the recordings from last year are also available, and they will appear on the campus. When Maria was teaching these first 2 weeks that I will do now, so we can have both versions. Yeah. Probably it will be better for you to watch. Fantastic video of Maria.
It's basically going to be very similar. I mean, the content of the subject has not changed, and most of the exercises are the same also. So it's alright if you want to just check into last year recordings, or it's up to you. Okay.
Also, if some problems arise, like today, if there is more recording, you still have recordings from last year.
Right. Actually, the class recordings are in YouTube, so this is available for anybody so it's okay. Anyway, so as you know from previous year, electromagnetism is everywhere. Okay. Basically, it's a part of physics that is connected to almost everything else that you can think of. Optics, thermodynamics, quantum mechanics, all of it. And basically, the main objective of our subject is to sort of try and understand the laws of electromagnetism, and in particular, being able to calculate and understand what kind of fields result from any given distribution of sources, typically charges or currents, as you know. Okay, so we do a lot of emphasis during the course on being able to basically calculate from the sources all the way up to the fields how any given charge or current present in any part of the universe modifies and creates an energy and a field around it. Okay. By the way, the opposite problem, like if we can measure and we know what a field is like, know what the sources are and where are they and the distribution, it's actually a very, very difficult one in physics. We will not be able to solve it most of the time, right? But we try to at least do the other way around, okay? So what we will do is first address electrostatics, meaning having a finite and well, typically finite, it can be infinite sometimes, or mostly finite, a distribution of static charges that generate electric fields around them that do not change in time, and being able to calculate those fields. We'll have a number of tools. We'll also work on magnetostatics, which will have, which will basically consist on having a stationary density of currents. By stationary means that the currents don't change over time. But obviously, if there is an electric current, there is a flow of current, things are not static anymore. But at least they are stationary in time, and then calculate the magnetic fields that result from them. We will do this in vacuum and also in the presence of matter, and this is going to be the new part for you, because you already did a little bit of electrostatics and magnetostatics, mostly in vacuum last year, but you did not put the presence of matter, I mean atoms, in the, let's say, in the space where these fields are being generated, right? So we'll do a lot of emphasis on this, and then at the very, very, very last part of the subject, we will put time into the equation and study induction effects and other kinds of sources of electromagnetic fields. All right, they're not just charges and currents, but there's also fields that change with time, generate other fields. You know Faraday's law, right? So we'll go into that. It's actually quite desirable if you have your physics 2 fundamentals clear, and also you will need, we will have some math, okay? I know how many of you come from the double degree? Okay, a few, fine. The guys and girls in physics, you have already done in the first year integral and derivative calculus in three-dimensional space. But you people in the double degree have not. But that's okay. We are going to use it, but that's going to be okay. Because this very first part of the subject is actually just math, mostly, right? So we'll give you the basics on how to do integrals and such, and changes between systems of coordinates, spherical, cylindrical, and all of those that we will need. And it will be also it will be a good tool, and we'll go over things which are good for people in the physics degree. Oh, okay, that's better. All right. Anyhow, so don't worry about it. You have to put a bit more work into it, but it's going to be really very easy. It's straightforward, okay? And Norbert has promised that he will not use tensor notation. Anyway, we'll go over tensor notation. So what's about the subject? There are 6 sections in this class. The first one will be basically going a bit over math and multidimensional calculus and integral calculus, and talk a little bit about the Gauss theorem, Stokes theorem, I mean theorems and expressions that we will need for calculating stuff later. And actually, there is going to be an interesting thing that none of you have seen so far at the end of the section, which is talking about the Dirac delta function, which we will need to describe point charges, and it's a very important one in physics. Okay, so it's very likely that this is going to be your first exposure to this function, which isn't really a function, but anyhow, we are physicists, most of us, so we don't care a lot about that, but we'll need it, okay? And then the second section, which is what I will come back, it's going to be electrostatics in vacuum. You already know a lot of this. As a matter of fact, I would dare saying that 80% of the things we'll go over, they are already going to be familiar. So the most important part of the section for you is going to be being familiar with how the notation we will use and how we calculate integrals and stuff in 3 dimensions, and a bit of differential calculus. Last year you saw the Maxwell equations in integral form, right? But you did not see the differential form with rotationals and curves and divergences. Okay, we'll do this. So that will be probably the newest part for you. And then we'll also talk about multiple expansions of the electrostatic potential, which are just mathematical methods to calculate difficult potentials, difficult is quoting, right? Which is also probably going to be you, which is okay. The third part of our subject, section 3, electrostatic fields in matter, this is new for you. You've seen a little bit of it last year when you were thinking about putting dielectrics into capacitors, which was so much fun, right? We'll do a lot of it. Sorry. But we'll insist a lot on the physics, on how things change, how the fields change when you have matter, which is basically charges, protons and electrons, everywhere. All right? And talk about the concept of polarization, which you probably don't know, right? And basically, it's like a generalization of electrostatics just when you have a lot of chapters and that you are inside matter, which is, matter is everywhere in this universe, so you need to be aware of it. So in some respect, this section 3 is a generalization of section 2. And here it's the end of what we will call electrostatics. Here, okay? Every single year in the exams, we have some problem or question of this. This is a very important section, because if you control this one, it means you control that one too, as well. And as a matter of fact, we do calculations where you have a distribution of charge and you have to calculate the fields everywhere, inside a distribution and outside, and that's vacuum. So basically, it includes everything. We'll talk about the concept of displacement vector, which is like sort of an electric field, not really, but anyhow, in the presence of matter, right? And that will be basically the first half. Then section 4 will go into magnetostatics, which is going to be calculation of magnetic fields in the presence of stationary currents mostly. A lot of it you already know, like the law of Biot-Savart and all of those things, which are so much fun, right? But then basically that's the most important part of it when you talk about the differential and integral formulations of the field, and again relate the fields to their forces. How we'll get there. And the new concept here is going to be the magnetic vector potential. This one you don't know. How do you? There is an electrostatic potential that you know, scalar, and the gradient of it is the electric field, well, minus the electric field. There is also a magnetic potential vector. And the rotational, the curve of it, is the magnetic field. At the end of the day, when you finish the whole second year, you will know that the electric and magnetic fields are pretty much the same thing. They're sort of like the two sides of a given coin, right? So there also has to be some sort of potential related to the magnetic field. It's a vector one. But anyhow, we'll talk about it in section 4. And it also has like multiple expansion and that much. Anyway, section 5, surprise, surprise, is going to be the generalization of section 4, but in the presence of matter. And how do we write magnetic fields? When we have matter, and you know there are atoms, and there are electrons, and they move, and they are also like microscopic currents, things happen. New things happen. That will be it. Electrostatics, magnetostatics, and then electromagnetic fields and Maxwell equations. Here we put time into the equation. Okay? Time varying fields are a source of other fields. Time varying electric fields generate magnetic fields. Time varying magnetic fields generate electric fields. Just like the Faraday law. Okay? So we write also the equivalent of the Faraday law, but for electric fields depend on that. You probably saw a little bit of this last year, which gives rise to displacement currents. You remember at the end of, well, no, don't worry, that's fine. If you don't remember anything, it's probably much better actually. So that's okay. Okay, so then we can talk about things and don't have to fight again your previous ideas of things that might be right or might be wrong or whatever, right? And that will be the end of it. After this, you go into Electromagnetism II, which is something from the second semester, and you start solving the Maxwell equations that will write completely here, and then talk about fields that propagate in the form of waves and stuff, but that will be your next problem. So let's do one battle at a time, all right? So that's Electromagnetism I. And then, sorry. All right, sorry. Okay, then the good news about this subject, and actually this is going to be common to most of the other electromagnetism classes, the other groups, is that there is a book, a single book, which is actually quite good to follow the subject. Quite good, meaning most of the things we are going to see, you can see them in this book, at the very precise same level of complexity that we will use in the class, okay? I would say 90% of the things are in here. So this is a subject where you can actually go and get one book. It's this one. Introduction to Electrodynamics, Dave Griffiths. And you will probably also use it for Electromagnetism too, right?
Yeah.
So if you have to buy a book, or get it. I mean, I have to say buy it, all right? But you have other ways of getting books anyway, it's not my problem. It's this one. Now, a few other things will probably be also be interesting to look in other sources, and as a matter of fact, I will strongly recommend that you get used to looking at different books, different things in different books, with different notation, with different everything. Don't get used to a single scheme. In physics, you're going to need to be able to switch and develop your tolerance to ambiguity, let's say, because sometimes you have to think outside the box, and this is a way of actually learning to do that. But at least to study, this is a good one if you have to get only one to get your hands on. Okay?
Let me impress upon this point. This book, Jackson's book, contains everything we ever wanted to know about electrodynamics. It contains more than Griffith's book. The difference is, from this book you can study, you can understand what he's saying, and you can learn. From this book, after 10 years of going through it again and again, I start to understand something. So, this is a great book, but you should really start with this one.
Yes, I can insist on that. This is the Bible, okay? But it's just like the, well, no, I was going to say like the Landau books in mechanics, that you read like the first 3 lines and you're thinking on them for like 3 weeks and you never go to the second paragraph. Anyhow, this is really the book, but it's not useful for you at this point. But if you have a chance to once in a while go check things in here, it's a good way of getting used to the book with capital letters. Okay. There are other things on electromagnetic like this Samuel book, which is also a bit of a higher level than we will do here, but maybe it's a bit more readable. I mean, user-friendly than this one. All right. But anyway, for the time being, the Griffiths, it's fine. I lost this. It's here. All right. So there are a lot of other additional resources, and like I said, we'll put in the virtual campus all of the materials that are more relevant than lots of any. I mean, classical electromagnetism is relatively old. I mean, it's old enough that any book is right. Okay, it's not like other branches of physics where then there is this theory, and then there is the next theory, and then there is somebody coming and proving the other guy wrong. No, electromagnetism has been there since the 19th century, so we have a lot of time to fix things. But there are a couple of useful things here, maybe from books on solved exercises. This one by Eloisa Núñez, this is in the library, or Victoriano López. I feel that can be interesting. Fernández, Problemas de Campos Electromagnéticos. Those can be helpful. They are in the library, correct? By the way, a lot of them are in English and a lot of them are in Spanish, and this is live. You know. Oh, one thing we didn't say. This is of course the English class, but it's English for us, right? If you want to make a question and you are not sure that you find the right words or whatever, or just want to talk about it in Spanish, feel free to use Spanish. Okay? Let the language not be a barrier for communication. And if you want to come to an office session or have some, and you want to talk in Spanish because it's more comfortable for you, it's all right for us, okay? At least for me, I understand. And as a matter of fact, if we have already posted in the campus the first collection of exercises, you will see that they are in English and then in Spanish. So just don't, this is a class of physics. It's not a class of English, and actually I'm sure that maybe 50 or 99% or maybe 100% of you speak better English than I do. So I'm not an English teacher, I don't mean to be. Okay? So please, we have to give this class in English because it's supposed to be like that. But for you, and the exams, we'll talk about the exams in a moment, but you can also write them in Spanish if you want to. Same goes for homework. Now, the one only thing that we ask of you is if you choose one, English or Spanish, or through the whole exam in English or Spanish. Don't change like you know, halfway through the exercise. Okay? So that's okay. We are not going to grade you on your English. Right? Okay. Going then. Next thing. Well, this information is in the campus. Other places where you can find the apps and stuff on electromagnetism, which will be useful. This is the probable schedule for the subject, so you can have an idea of more or less when we're going to do what. By the way, this subject, every single section relies on everything that we have previously seen, meaning they are not orthogonal to each other, the different sections. If you don't understand section 2, you will never get a hold on section 3. It's gone. Or it goes without saying section 6. So do, please, by all means, not let go of the subject and think that a month from now you can catch up. It's not going to happen. Especially since you have a lot of other things that you also have to take care of, I mean the other classes, right? So what we will try to do is pretty much give you homework every week or every other week. It will be easy, it will be like mostly problems or activities related to what we are doing, so we make sure that at least weekly, or maybe every other week, you sit down with your notes and your book or whatever, and at least go over the materials, because otherwise you will not be able to follow. As a matter of fact, if the exam was only one problem, and we want to do an exam that was only one long exercise, it will be on section 6. It contains everything else. If you can do this, you can do this. Okay? So please stay tuned, don't let go of it. And I can also say, as you probably know already, that if you go over the whole continuous evaluation and determine the homework and such with us, it's not difficult to pass the subject. Because you will work through the whole semester. You get to the exam, you know what you're doing. Okay. So, anyhow, this first couple of weeks is going to be Norbert teaching section 1. And then the next 3 weeks, basically we'll go over electrostatics in vacuum. Till the end of October, more or less, matter, electrostatics in matter, the presence of matter. And then we will spend November and December doing magnetostatics and electromagnetism the last couple of weeks. This is an approximate schedule, plus minus a couple of days, because we have not had into account that there are a number of holidays here and there, but anyhow. So you more or less have an idea on what is the time print that we're going to follow. All right? You will say, well, we're spending a lot of time in electrostatics here, which is very boring, and it's true. However, the mathematical tools mainly that we will train during this part are going to be so useful for these other parts that it's actually, it's worth it. Okay, because then we can go over magnetostatics and matter. I mean, and you will only work on the physics, not on the math. Okay, so it's going to be a bit slower in the beginning and then a bit faster at the end. But we should get to the end of the everything.
Electrostatics is such a broad subject that a good chunk of it didn't fit into this course, so you will get it in electromagnetism too. And even then, you will not be at the level of an electrical engineer who can solve problems much better than you will ever do. But you can solve different types of problems than an engineer.
Okay, this is an interesting part. Evaluation, grading. What are we going to do? This subject has a final exam, just like all the others. Okay, it will take place in January. I think it's January 17th, but we'll check about that later. In principle, your final mark can be either 100% what you get in the final exam, or 80% exam plus 20% other things, meaning the continuous evaluation. We will pick for each one of you the highest of those two numbers, and then that will be your final score. So you can go for both. In other words, I strongly recommend that you follow up the other activities that will be either homework or I will have to think about it. Every year we change that part a little bit, or maybe some activities, some presentations, some group. I don't know. We'll see. Okay, we'll see as we go. Mostly, unfortunately, will be homework. That maybe some exercise that you have to turn in. And by the way, I can only keep insisting that please do the homework. Turn it in. You'll get to the end of the semester with 2 points in your pocket. Those are yours. And after you have it too, it's very easy to get on the way up to the 5. Okay?
Also the correlations between those students who turn in their homeworks regularly and those who get very high grades in the final exam is very high. So in that sense, in the end of the day, you may say, okay, my exam is better than the combined average, but it's better because you were working so hard.
And then there is another thing with the homework. You do not need to copy, because we don't really care too much about you getting the homework perfect. As a matter of fact, for me, it's very helpful when there is some mistake, and so I see what parts you didn't really understand or whatever. I'm going to give you a 10 in the homework, just if you turn it in. So you have 100% of the grade already just by trying to do the problem and giving it to me, even if you don't get to the right solution. So you don't need to just copy from other people. Just really sit down, think about it, go over your notes, and try get it done on your own. Even if you fail, you'll get 100%. Okay? Do not copy. You don't need to. It's good. I mean, you learn a lot more about things when you fail than when you succeed, because then you know what you don't know. If that makes any sense. And that will help you improve. Now, that said, of course, there is always a few of you that go a little bit over what I was asking for. For some problem on a given thing, just have this whatever charge distribution, calculate whatever field, and solve these few questions. And then there is always someone that comes and says, well, I did write a little script, and I actually simulated the field, and I plotted it around the areas of interest, and this is what I get. Oh, excellent, now you have 120% of the grade. So actually, there is a lot of people who get to the end of the semester with not 10, 2 points, but maybe 2.5 or 3, and that makes a difference. So if at any point with the homework you feel that you can go a little bit over what I'm asking for, that will get you over the final deadline or 100% line. Feel free to do it and be creative about it, and anything you can think of that could be relevant to a given problem, just if you want to play around with it, just do it. Oh, I did calculate this other possibility that was not in the problem, but actually what happens if somebody comes in terms of the light? Well, these are the fields now, whatever, I don't care. Feel free to go over what we are asking for, because you will actually get an extra for that. And as a matter of fact, in the last few years, most people that got the matricular honor had an 11 point something, right? because they actually, that's when we really see how much over the minimum requisites you went, right? So like I said, if you get the homework done, even if it's wrong, you get a 10. Now you can get a 12 or 13 if you will. Feel free to be creative about it. Anything you can think of, okay?
Do you need a minimum grade in the final?
Yes, of course, you need to get a 5. I mean, to pass the subject, you need to go over a 5 of final grade, being the maximum of 100% exam or 80% exam plus 20% other things.
Yeah, but I mean, I do have like a 4 in the final test, and with the 2 points below a 5.
Oh, I see. So the question is whether you need to whether there is a critical threshold over which the continuous evaluation is not useful, like a 4. The answer is no, right?
Well, in other, if you read the guide in other subjects, like in electrodynamics, it says that if your final exam is a 3.5, that's your final grade, or if it's less.
Okay.
So then they don't add but
Okay.
in a way, if you get a 2 on the final exam, then no matter how much you got in the continuous evaluation, it will not help you.
Right.
And if you get a 4 in the final exam and you have a lot of continuous evaluation, then you will be fine.
So there is no critical threshold for the grade as long as you go over a 5 in the combined weight of things. Imagine that you have a 5 in the final exam, just, and you have 100% in the continuous evaluation. Then you basically are passed. If you have a 4 in the final exam and 100% in the continuous evaluation, you are passed. If you have 3.5 in the final exam and 150% in the continuous evaluation, you pass. Okay? Now, if you get a 1 in the final exam and 100% in the continuous evaluation, there is no way on earth to pass. The thing is that actually working on that, on those other activities, will help you get through the final exam. That's the idea. All right? By the way, people at home, if you have any questions, just ask them or put them in the chat, okay? But in a moment, we'll actually have you have time to ask questions. So, like I said, this is pretty much what we said about the evaluation. It's in this slide. All right. For the students, the evaluation will be either 100% final exam or 80% final exam, and then 20% other things that we will discuss as we go. And of course, you can also evaluate us in the Docencia online evaluation when the time comes. Feel free to do it. And that's about it. One other thing that I didn't put here, but we do it every year, so most likely we'll keep doing it, is the final exam will actually consist of a problem or two and a few shorter questions. We typically allow you to use a book, one book, which most people actually use the Griffiths. So it's not like you have to learn everything by heart and then come to the exam and write like 3 pages of exercise. You have tools that you can use for formulae, for example. Okay, so in this respect, you need to show that you learn physics, not that you have a really big book base in your head, which is a very good thing. But anyway, that will do. That said, one other thing. Almost every year, we have done like a partial exam at the middle of the semester, which is typically going to be the first block, electrostatics. Okay? Like you did in the first year. In the second year, it's not mandatory. As a matter of fact, some classes don't do it. So think about if you want to do it, and we'll talk about it when the time comes, whether you want to do it or not. Good things about the partial exam, it's a good place to actually sit down and study and catch up with the whole block of electrostatics. It could count for the continuous evaluation, or since we think it's actually a good idea that we do this exam, we can twist your arm a little bit behind your back and give you some extra point or something for the, doing this exam. So at most years, you people want to do this. I think it's a good thing, but we talk about it as we go. It's not mandatory. We don't have to do it. As a matter of fact, some classes don't do it at all. Other things. The exam
it also doesn't eliminate anything from your final exam, so it's not like...
Right, it's just an opportunity to catch up. Okay, and just sit down and make sure that you have this part covered. And then other things that are important, the final exam is not going to be common with other classes. So we'll have our own problems and our own, this is also different from last year. In the first year, I think, like you will sit down and do the same, we're not gonna do this. All right, so again, focus on the class and just go through your subject. Anything else you want to add? Any other questions from you or people at home? No? Anyway, like I said, anytime just feel free to raise your hand and ask questions regarding, of course, the materials of the class or how things are going to work, or if you don't have, at some point we'll also probably open some question. Well, I don't know how we'll do this, but since we're going to do this halfway thing at home and here, and for you it's a new method, we want to know whether you have any ideas on how to improve the methodology, or things that are not working for you, or whether you are at home and you don't follow attention, or whether you are in the class. I don't know. So we're going to give maybe section 1 and 2, and then probably open some sort of discussion forum at some point, either here or in Virtual Campus, to see whether there is a way for you to give us input on what things you think could be done better at some point. But if you have any ideas at any point, or like, for example, someone was saying, we cannot hear you, well, just say it anytime. Okay, we're here to help you, not to grill you. Okay, and this said, I'm done, right? Okay. So normally we'll stay with you for the next couple of weeks, and then I will come back, and well, we'll find a way to make this work. Okay? Any question? Yes, so no, there is a class today, okay? All right, I'll see you soon.
Bye. So, for people at home, I would like to ask you one thing. I'm very bad at focusing my attention in different places, unlike Maria. So instead of writing in the chat box any question, please just shout, turn on your microphone when you need to ask a question, and just ask. Hopefully this makes a sound. Maybe you could test it. Maybe someone could say something from home, but sometimes it is linked onto the volume setup. Anyone? But I don't hear anything. Maybe that's not working. So then just write your question in the chat box, and at some point get a chance to do it. Also, Maria has excellent PowerPoint presentations prepared for you, like this one, and it's available for you on the campus you've got. And I will follow these things, but I will not go through them in class. You can see the videos of Maria going through these slides, so you don't actually lose anything. I just don't like to give a class like this, because if I have this PowerPoint, then I go through it very fast. That's not good for you. So I'm going to use the Blackboard, and I will not be able to cover everything, but you will also not lose anything. So just to look at it quickly, what I'm going to be dealing with is these first two lines here. No, it's all of this for me, right? So we start with coordinate systems, and we end up with the direct delta functional. If you are from the math faculty, then it's functional. But for us, it's just a function. And we need to see all of these things. And there are words here that you might not know what they mean. The circulation, the divergence, the curl, the Laplacian, and the direct delta. Are you familiar with these things? Have you seen them? Some of you? Can you do calculations using the curl of a vector field, things like that? So these things we will need for electromagnetism, and that is my job to help you do actual calculations. And with that, I'm gonna do this. I'm gonna erase this. Turn off the vector, and it's done. So it's not going to be so also for people from home, I need to know up to what point you can see the blackboard. My turn. Can I write here?
Yeah, we can see that.
I can see the little line. I don't get much response from those guys, but you are here. So, your goal for this course is to get to see Maxwell's equations. You already know Maxwell's equations, but I'm going to write them in a different form. We will see something like this. The divergence of the electric field is the charge density. You know this as Gauss's law. If you have a certain amount of charge, they create an electric field, you do an integral over some surface, and that has to do with the charge inside. That was the integral form, and this is the thing that we need to learn, what this thing means. It's called the divergence. Sometimes it's written as the divergence of the electric field. This thing and this thing are the same thing. We also have to know what these little triangles mean. It's not like a version of the stop sign on the street, but it looks similar. Then we have another equation for Ampere's law. So how do you write Ampere's law? Ampere's law says that electrical currents create a magnetic field. Again, we will use the little triangle, but we will do something that looks like the vector product with the magnetic field. And that will be, instead of the current, it will be the current density plus the sign derivative of the electric field, which was the famous contribution by Maxwell. So Maxwell's equations existed before Maxwell, but he added this just because he felt like it, and there was light. So light, electromagnetic radiation, is the consequence of having this term. It's very important. You might have seen it, or you will definitely see it. Questions?
What is the mu multiplying?
So this thing here is what we have to learn. I mean, all of these things Maria will explain in some other sections, but what I have to do is tell you what this thing means and how to use it. And that sometimes is written as the curl of B, sometimes it's written as the rotational of B. They mean the same thing. Okay, so this thing, and this thing are the same thing. And then you have the Maxwell's equation, which says that there are no magnetic monopoles. So this and this look similar, but the electrical field has sources, the charges. The magnetic field doesn't have sources. So this equation actually means, and we have to see how this equation means that the magnetic field lines close onto each other. So these little squiggles actually mean something physically, and this is our interest. What's the physical meaning? And the final equation is Faraday's law, which again has to do with the rotational or the curl, in this case of the electrical field. And it says that changing magnetic fields create a voltage. This is Faraday's law, right? But we didn't write voltage here, we wrote the electric field, and we wrote something strange about the electric field. So vector fields, the electric field, the magnetic field, the current density, they are vector fields. I will tell you what the vector field is. Have some local properties that are important. You have seen these things in integral form, but they really do have properties locally that are relevant. So, on top of this, you already know that the electric field is the gradient of the scalar potential, at least in electrostatics. You will see that in reality you will have to add the time derivative of something new, which is the vector potential. Maria told you that you will see the vector potential. So this is just a time derivative. There's nothing new for us here, mathematically speaking. But we have to see how this is the gradient. So when I write this, I am talking about the gradient of phi, of some potential. And the magnetic field will again use the rotational of the magnetic vector potential. So basically, this is the math that we have to learn. What does this thing mean? What happens when I write a little triangle in front of a scalar field? What happens when I write a little triangle in something that looks like a scalar product with a vector field? And what happens when I try to do something that looks like the vector product with a vector field? We will not see all of this today, but this is our plan. Then, the Dirac delta, I tell you what the Dirac delta is used for, and then we will see how to use it in reality. If I have some charges here and there, positive, negative, and another positive, so they are fixed charges, right? I have charge Q1 here, Q2 here, Q3 here. So I have a charge Q1 at the position R1, right? And it might even vary. If the charge moves around, not in the first section of the class, but afterwards, come November, they will move around. Charge 2 will also be at the vector position R2. So these are vectors, and this thing is how I write the letter R. I'm sorry about it. My handwriting is not the greatest. When you see something on the board and you don't know what letter it means, just ask. So this is easy to understand. I have some charges, they are at some spots. Okay. But here, I was talking about the charge density. The density of the charge is not the charge itself. If I have a continuously charged dielectric sphere, for example, there's charge everywhere within the sphere and nothing outside. So the charge density would be some value within the sphere and nothing outside. Within the sphere, it might be homogeneous. If I have a metallic sphere, then there is a charge only on the surface, nothing inside and nothing outside. How can I, and if I have these point charges, then I have charge only at these points and nothing anywhere else. So the question is, how can I describe these charges using this language? What's the density of a point charge? There's no density here. Rho is 0 here, it's 0 here, it's 0 in between, it's 0 everywhere. But it's not 0 here or here. So what is it? Right? The density, normally, and this is my letter rho. I'm sorry, I just write a little circle on the VD line, but I know that's not how you are supposed to write it. Rho, again, would be something that varies in space and time. And you define it locally as taking the amount of charge that you have in a small volume, right? So that's okay. That's kind of like a derivative. You take a limit if you're a mathematician and you do your thing. But that's the basic idea of any density, be it a charge density or some other kind of density. If I do that here, I draw a little imaginary box around my charge that has a certain volume, and there is some charge in it. Okay, so I get a number. Then I draw a smaller box. The Q will not change because it's the charge that I have here, which has a fixed value, Q1. But the volume has changed, it's smaller. So the number I get will depend on delta V. That's not the case in my continuously charged sphere, because the amount of charge will depend on the tiny little volume that I have. So I will convert. Here, I will not convert. I will get a bigger and bigger number as I decrease delta V. But I still want to describe this situation because I want to talk about point charges, electrons, protons, whatever. Even just imaginary point charges that I deal with in my electrostatics programs. And this is where the Dirac delta comes in. So in physics, we like to use this delta function, which depends on, for example, the spatial positions, or it could depend on time. It can depend on anything. The idea of the Dirac delta is, if I write this, then its value is 0 when the position vector is not in the origin. Okay, so that's okay. But it's infinite in the center. That doesn't in the center. Okay, that sounds good, but it doesn't quite make much sense. So we have to do a little bit of better definition. So what we do is the following. You take the integral of the delta function and let me just, instead of any position, I will use it as we normally use it at some point in space, a fixed point, and then we do an integral. If I do this, then I just get 1, or maybe 4 pi. That depends on your book. Sometimes it gives you 4 pi. Even better, if I multiply it by some function f, which also depends on space, then I will get the value of f at the position r0. So that's great. What the delta function does, as long as you use it in an integral, it will just pick out the value of whatever else is in the integral at this point. And then you can use it to describe these charges. So the charge density corresponding to these 4 charges would just be the sum over these 4 charges. The letter I will go through 1, 2, 3, 4, because I had 4, and we will just place a delta function at the position of the charges. Okay, so this is what the delta function will be. Obviously, I have not taught you how to use a delta function and what it really is. In 2 weeks' time, I will do so. But this is where we want to get to, and this is the point of the delta function. If you want to imagine how a delta function is in 1 dimension, x, you could imagine drawing functions like this, right? You draw a function like this, and then you draw a function like this, and then you draw a function even more pointy. It goes up, and then comes down. And you draw a series of functions like this, maintaining their area. So the full integral of any of these lines will give you 1. And then the limiting function obviously is not a function because it's 0 everywhere and it's undefined at 0. But still, in the limiting sense, you can do these integrals, and they will work like this. And that is how a physicist defines a delta function. A mathematician talks about the functional. The functional is some animal that grabs hold of a whole function, f, and spits out 1 number. In that sense, the delta is not a function, it's a functional, but we are physicists, we don't care. We use the delta function as this. And in reality, we use it like this and we ignore the whole thing. So, if I want to talk about fields, let's say the current, let's suppose I have a river, right? These are the river banks. You can stand here and there is a flow. The flow of water will be like this, no? It flows fast in the middle and it doesn't flow much at the river, in the normal river. The ones that we have in Hungary behave like this. I'm Hungarian, so I will sometimes use Hungarian analogies. So you can imagine that the size of these arrows refer to the flow or the water velocity that passes through here. So that is a field. I'm describing some quantity, which is the velocity, that depends at least on the position if I have laminar flow. It might depend on time as well if I have turbulence, right? If I have eddies, I have whirlpools, they will move around. So then this field will depend on both the position and on the time. So just so that we don't talk about electromagnetic quantities, you can also imagine the water flow. And I want to talk about the properties of this field. I somehow want to see what these changes in space mean and how I can interpret them. Also, I want to decide what sort of coordinate system to use. And so what I want to talk about now is the coordinate system. The system of coordinates for something like this would be perfectly fine to use Cartesian systems, right? So I will have a main axis here, another axis here, and maybe I want to use something that goes in the depth of the river. And if it's a real river, that's not just a few centimeters deep, I might have to do that. So I will use a Cartesian system. So I can describe the velocity as some number dx, which is the length of these vectors that I drew. And then we will use the unit vector ux. I want to write just x, but I saw that Maria uses ux. So that will be the little vector that has a length of 1 and is pointing along the x direction. Plus, you might have some component of the flow. Let's say there is a rock here, and then the flow starts to diverge like this because it cannot go through here. Then you will have a component in the y direction too. You might have to use that as well. Also, you may have noticed I have the bad habit of indicating a vector with a line underneath. I am aware that I should put it up there, but I just can't bring myself to it. And then, if it's a true whirlpool, it might have a component going down, which might suck the wind. So you describe your vector field, the velocity, everywhere in space using Cartesian systems. For unit vectors, I tend to use a little hat above the vectors that is fairly general notation. Okay. Now, if I have, let's say, a line of current, and I want to describe the magnetic field around it, we all know how the magnetic field looks something like this. I could describe these magnetic fields using the Cartesian system. I would probably choose the z-axis to be parallel to the current, and then the xy axis would describe the circle somehow. Okay, I can do that, of course. Any coordinate system can describe any sort of field. But it would be painful. It's not ideal. So, instead of that, I might want to use cylindrical coordinates. In cylindrical coordinates, I will still use the uz along some line, which I will try to use to coincide with the physically important thing. And then I will use a radial field, a radial unit vector, u of r. But that one depends on where I am. It will point in different directions because it's radial. It's always pointing from the central line towards wherever. And then I will use what is the azimuthal vector. So it's something that points precisely along these circular lines. If I have circular lines in my problem, then it's a good choice. So they end up forming orthogonal systems. Not all coordinate systems are orthogonal. We will use only orthogonal ones, and they will have unitary vectors. Not all coordinate systems have unitary elements, but these ones do. So we will have to learn how to deal with cylindrical systems tomorrow. And the last one that I might want to use, if I have precisely these point charges, I want to describe the electrical field or some other quantity, those vector lines will do this, okay? They will come out radially. I know that already because we have studied physics. So I can describe this in a Cartesian system, of course. I could also decide to describe it in a cylindrical system. I can do that. Both of these will be fairly painful, especially in the cylindrical. It would be better to choose a coordinate system that adapts to the symmetry of my problem. And that one, of course, is the spherical coordinate system. So I can imagine some sphere here. I will use one unit vector which is radial, u of r, so it always points from the center to wherever it needs to point. So it's great because it will be parallel to my actual physical electrical field lines, if I'm lucky, not every time, but for one solitary charge it will be. And then I will have to choose an axis, a main axis, but I will not orient my unit vector along this main axis, but what I will do is I will use this angle, which is usually called the angle theta, and I will orient my unitary vector tangential to it, tangential to the sphere locally in this plane. So wherever it is. So if I come out of the blackboard, then my unitary vector will also turn, because it will remain in this plane, in the point where I am on the sphere and my chosen axis. And that will be the polar angle. So I will have u of theta. And I will have to make a projection of the point where I am to the plane perpendicular to my chosen axis that goes through the center point. I will make a projection and I will choose the last vector to be perpendicular to it. So it will depend on this angle that I moved out of the plane from with. And that will be the unitary vector phi. These three again are unitary and they are orthogonal. But all three of them keep changing with position. And so I will have to learn how to go from one system to the other, because the actual field is the same. The actual physical quantity does not depend on how I choose to describe it. So it's like using different languages to talk about the same thing, and sometimes one is more convenient than the other is. And so not today, but we will look at it, how to go from one to the other, and vice versa. That's not so bad. That's just having a little bit of geometry and a little bit of stereo vision, which I suppose all of you have. But then we will have to follow with our derivatives, with the gradient, with the divergence, with the curl. And they can also, they are relatively easy to describe in Cartesian coordinate systems. But their meaning is not dependent on our coordinate system. And so we have to learn how to describe them in cylindrical and spherical. And the formulae for something like the curl in spherical are fairly complex. You have tables for it, and no one in their right mind would try to calculate it every time. That's why you have tables. But it's good to try it once or twice to see how the table came about. So instead of following the transparencies, I will just try to do some of these calculations here and do them together. That will be the plan for the next few days. And with that, I I finish for today, and then we meet again at 11 tomorrow.